Hello, I'm Myra,
And hello, I'm William.
and we are from Team Magic Stinger. For our project, we are investigating propulsion methods for fast interplanetary travel. In our research, specific impulse plays a significant role in our analysis. So today, our lesson will discuss the concept of specific impulse. Specific impulse is also abbreviated as ISP, and we will refer to specific impulse as ISP throughout this presentation.
If you ever look up information about propulsion systems, specific impulse is a statistic that you are likely to come across, and that's because specific impulse is a measurement of rocket performance. Specific impulse is a number that describes the efficiency of a rocket, and you can think of it as a rocket's version of miles per gallon in a car. From specific impulse, we can understand a few factors. We can understand the efficiency of a rocket. We can understand the quantity of fuel that we need, the size of the engine, and from specific impulse, we learn that it is measured in seconds. There is no unit conversion needed. It can help to determine the thrust of a rocket, and it can determine if the rocket is a sprinter or a marathon runner. But we'll get into that later.
Specific impulse is a useful measurement because it can allow us to determine approximately how much fuel would be needed on a given mission. It can also be used to find an approximate size of the engine. By dividing required thrust by specific impulse, we can find the weight flow of propellant that the engine requires, and therefore find an approximate size of the engine.
Specific impulse is measured in seconds. This measurement is convenient because the same number will be achieved regardless if it is calculated using English or metric units. Essentially, it requires no unit conversion, which simplifies the math. Knowing specific impulse creates a quick way to determine the thrust of a rocket. If the mass flow rate is known as well as the specific impulse, thrust can be calculated.
Lastly, specific impulse is an indicator of the performance of a propulsion system. With a high specific impulse, you can get to a certain velocity over a longer period of time while using less fuel. Think of it as a marathon runner. Contrastly, with low specific impulse, you can reach a certain thrust quickly. However, you can't maintain it, and in the long run, you burn more fuel. Think of it as a sprinter. Sprinters can run at a high velocity, but only for a short time. They cannot maintain that high velocity over a long distance, say the length of a marathon.
Before we get into calculating specific impulse, here are some variables that we will need to know. First, we have thrust, which is a force that pushes the rocket. Next, we have mass flow rate, the mass of propellant that leaves the engine over time, and impulse, which is the average thrust times the total time of firing.
Next, we have actual exhaust velocity, which is the average speed that the propellant leaves the vehicle. Next is effective exhaust velocity, which is the exhaust velocity needed to produce the same thrust as the actual exhaust velocity. When rockets are operating in a vacuum, these two measurements are the same and proportional to specific impulse. Exhaust velocity is also known as exit velocity, and in the upcoming calculations in the following slides, we will refer to it as exit velocity.
So, to calculate specific impulse, we can first start with the thrust equation for rockets. Thrust equals the mass flow rate times the exit velocity added to the product of the pressure distance across the engine and the engine area. Dividing by the mass flow rate, we obtain the equivalent velocity, which is the exit velocity plus the pressure difference across the engine times the engine area divided by the mass flow rate. By multiplying by mass flow rate again and substituting, we understand a new thrust equation, which is thrust equals equivalent velocity times mass flow rate.
Total impulse is defined as thrust multiplied by the total time. It can be written as an integral because it changes with time. When we substitute from the thrust equation, we get the integral of the equivalent velocity multiplied times the mass flow rate. We can assume that equivalent velocity remains constant over time and integrate to get total mass of propellant times equivalent velocity. The term specific means divided by weight. So we divide the impulse by the total mass of propellant times the gravitational acceleration constant. We can substitute to obtain equivalent velocity over gravitational acceleration constant and simplify to find that the specific impulse is equal to the thrust divided by the mass flow rate times the gravitational acceleration constant.
So let's take a look at a sample problem. A rocket engine produces a thrust of 1,000 kilonewtons at sea level with a propellant flow rate of 400 kilograms per second. Calculate the specific impulse. From the problem above, we are given a thrust of 1 million newtons and a propellant flow rate of 400 kilograms. Now remembering specific impulse is equal to thrust divided by propellant flow rate times the gravitational constant, we understand that specific impulse is equal to 1 million divided by 400 kilograms times gravitational constant of 9.8, and that gives us a specific impulse of 255 seconds at sea level. Now, why does this notion of sea level matter? Well, specific impulse changes with pressure and therefore has different values when measured in a vacuum versus, say, at sea level. And therefore, specific impulse is higher in a vacuum than at sea level.
Now, why is that? The reason that there is that difference can be related back to the thrust equation. If you recall, there was a pressure difference across the engine as a variable in the thrust equation. This causes overall the specific impulse to be higher in a vacuum than at sea level, as is exemplified by this table. Therefore, it is very important to state the pressure conditions of the specific impulse measurement. After reviewing the calculations, you can find some relationships between variables. First of all, a higher specific impulse means that less fuel is used and the engine is more efficient. Note that in the equation, the mass flow rate is in the denominator. This means that as the value increases, the specific impulse decreases because it is being divided by a larger value. Next, higher specific impulse leads to a greater potential for velocity, especially since larger specific impulse engines can provide thrust over a longer period of time. And finally, a lower specific impulse can reach a certain velocity quickly.
As we have already stated, high specific impulse is more efficient in the long run. The vehicle gets to a thrust over a longer period of time, whereas low specific impulse is less efficient for, say, interplanetary travel. That's because the vehicle gets to a thrust quickly, but it cannot maintain this thrust, and so it simply cruises. An example of this is seen in the Saturn V rocket. The first stage has a lower specific impulse, which would be helpful in the first stage of launch, getting outside of Earth's atmosphere, where a high velocity is needed quickly.
Specific impulse and thrust are frequently mentioned together. However, they are not exactly the same thing. Specific impulse is measured in seconds and gives us a way to determine how long it takes to get to a certain velocity. Thrust, on the other hand, is measured in newtons and tells the push the rocket is getting from a propellant. Although different measurements, specific impulse is related to thrust and is derived from the thrust equation. On the table to the right, we see different rocket types listed along with maximum specific impulse and maximum thrust. We can see that in rocket types with high maximum specific impulse, such as electric rockets, the thrust is lower. On the other hand, when the specific impulse is lower, such as with cold gas rockets, the maximum thrust is higher.
Here are some specific impulse values for some given engines. From the chart, we can see that solid and bipropellant rockets have low specific impulse compared to that of an ion thruster or a Vasmer engine. Now, the trade-off with this low specific impulse is a higher fuel mass because these systems require more fuel to operate. However, you will also notice the exhaust velocity from these low specific impulse systems is nowhere near the exhaust velocity of a higher specific impulse system.
Based on the previous table, it's easy to see that there is a relationship between the type of system and the specific impulse. Currently, organizations such as NASA are researching electrical propulsion and its advantages related to specific impulse. This is because electric propulsion tends to have higher specific impulse than chemical propulsion. Electric propulsion typically has a low thrust-to-mass ratio, but greater total impulse, which is achieved over longer durations. Unfortunately, the low thrust-to-mass ratio prevents electric propulsion systems from being able to be used to launch from Earth. In addition, electric propulsion requires large amounts of energy to operate. This places a limit on the size of specific impulse that can be produced. Nuclear or solar power options are currently being researched in order to help engines obtain their maximum specific impulse.
Chemical engines tend to have a high thrust-to-mass ratio, but low specific impulse. Now, this performance works well for launching from Earth, but is not reasonable for interplanetary travel. This is because it will require more fuel, and the more fuel it has, the more mass that it will obtain. Now, there are some characteristics of an engine that can influence the specific impulse. Here are 5 listed. They are the amount of chemical energy in the fuel, the efficiency of combustion, the shape of the nozzle, injector and combustion chambers, and pressure. As we've already noted, a change in pressure already affects specific impulse. But from these other characteristics, we'll explain how they can affect specific impulse. Injectors inject propellant and oxidizer into the combustion chamber at a proper rate. Now, the combustion chamber burns the propellant at high pressures, and the nozzle converts the energy from the combustion chamber into a kinetic energy. If a problem was to occur or a distribution error occurred, this would either positively affect the specific impulse or negatively affect the specific impulse.
So how does specific impulse relate to our project? Since the goal of our project is to analyze propulsion systems to determine the most feasible option for interplanetary travel, we want to ideally use as little fuel as possible to travel as fast as possible in space. Specific impulse is a measure of performance and efficiency, and so in our case, we are looking for high specific impulse. Higher specific impulse means more thrust for less propellant, which will lead to a lighter vehicle, less fuel, and more reasonable for interplanetary travel.
So in all, what is specific impulse? Specific impulse helps us to measure a rocket's efficiency. Specific impulse equals thrust divided by mass flow rate and gravitational acceleration. And specific impulse allows us to determine which engines are better suited for long distance space travel compared to short distance space travel.